Hello everyone, it's Arash from TU Berlin. So today I'm going to talk about our work on consistent hashing called Hash and Just. This is a joint work with my colleagues Chen, Avin, Robert Sama, Maryam, Shiran, and Stefan, Schmid. So let's dive in. To give you a glimpse of what our work does, our work is a combination of the traditional consistent hashing method and novel ideas that is used in the self-adjusting data structures. And in this presentation, we show why it's important to have self-adjusting variant of consistent hashing, what are the challenges, and how we did overcome that in our work. So consistent hashing is a traditional problem when we talk about load balancers, and it has been there. This problem has been studied for the last 30 years or so, and it has been used extensively in industry, for example, in Amazon, Apache, VMO, and so on. In this talk, we are mostly going to focus on the theoretical aspect of it, but we will get back into the practical aspect of it again at the end of the presentation. So the problem of consistent hashing is very relevant to another problem known as balls into bins. In that problem and in our problem, we have a set of M items or balls that we want to assign to a set of N servers, and we want this assignment to have some properties. So first of all, we want to ensure that the load or the number of items in each server is as uniform or as minimum as possible, and also the access cost to be low. And then we want to also allow for dynamic insertion and deletions of items on servers, and we want to be able to access items very quickly. So to provide all these properties, an idea was proposed in terms of consistent hashing. So this idea, we hash all the servers to the circle first. As you can see in this figure on the right, all the servers might not be equidistant on this unit circle. There might be different distances between two servers. And so having that in mind, we also assign the set of items to circle. These items might also not be assigned to the circle uniformly. And what we do is that we assign, if we have an item V, for example, as shown in the picture here, we will assign it to the next server in a clockwise manner, let's say here. And the server that contains an item V, we will call that server head of item V. And if we do the same thing again and again for all servers, we will end up with something like this. As you can see, the basic idea of the consistent hashing is just two arbitrary hash functions might result into very unbalanced loads. Therefore, there are, and this unbalanced load can be even result in a logarithmic gap between minimum and maximum load. To improve upon this, there were some ideas out there. So one of the most famous ones is called power of two choices. When you select two positions on the ring, and you would assign the item to the server which has a lower load. So this can be something to improve the load balancing, has been shown to have asymptotic improvement, but still the gap between the minimum and maximum values is not guaranteed to be constant. So to go towards this constant gap between maximum and minimum, recently a team at Google have proposed an idea is to bound the capacity of each server. So the minimum capacity, if we want to have the same capacity on all servers, the minimum capacity needed is m divided by n, the number of items divided by the number of servers. And they said, okay, let us augment this amount, let's say to set the capacity by beta times this minimum amount. As you can see, if we do this, for example, here, but by a factor of 1.75, this factor beta can be anything between 1 and 2 or beyond. And we might have some leftover items. What we do with these leftover items, we will move them again clockwise to the next server that has an available capacity to store these items. So this is how we assign these leftover items. And for example, when item A has been assigned to the next server, in order to search for it, we need to always start from the head. It's not the case that we can directly go to the server that currently holds an item. We need to, because we only know the hash function, we always need to start from the head of an item. And so one of the challenges here with this approach is that we still not reach the optimal load balancing that we can reach. And the other thing is that especially when beta is low, the number of servers that we need to search for an item can become large. So our idea is to, first of all, use an additional capacity, like a factor alpha plus 1, plus 2, plus 3 additional capacity on top of the minimum capacity that is needed. So we do the same thing. If there are some leftover items, we move them clockwise. And the other point here is that this is where our demand ever part comes into play, is that when we want to move some items, when we are searching for an item, we also bring it back to its own head. So if we had an item U here, we bring it back to its original head, where you should be looking for it step by step by moving items between servers. So here we can be as close to optimal storage utilization as possible. And considering the fact that the access cost to the first server, to the head of an item, is 1, and also a set of input sequences that are what we call well behaved, we can show that combining the access cost and reconfiguration cost of our algorithm, reconfiguration cost, I mean the part that we are moving back items to its head, combining these two costs and comparing the algorithms, an optimal algorithm that can do these two operations of access and reconfiguration, our algorithm will show that it's constant competitive. So to wrap up, the traditional algorithm has a very low access cost. It can find essentially everything in its own head, but it has a very high storage utilization. On the other hand, with bounded load improves this storage utilization by setting a cap on the capacity, but the access cost can become higher. So we want to get best of both worlds and have a low access cost and high storage utilization. So here I want to briefly go over our analysis. The full version of our analysis can be found in our paper. So the first thing is that if we assume that the cost of moving items between servers during the reconfiguration is omega times the cost of just searching for an item, our algorithm uh, is constant competitive by considering such a constant factor between moving and searching the items. So our proof has multiple steps. I mentioned two of them here. So the first one is that we show we can partition an instance of consistent hashing into a set of lists, what we call server list, because the difference between lists is that here we have capacity and items can come from multiple heads. And why we can do this decomposition is that because we assumed a little bit of extra capacity always. We have non-full servers, and during the access operations, we will not jump over these non-full servers. And one of the other observations that we have is that access cost inside this server list that has the fixed capacity and can have multiple heads is the access cost in each server list is constant competitive. So this can be done with potential function on a space and an inversion. And an inversion is the difference between the how we position items in our algorithm and how an optimal would position a pair of items relative to each other. So if one of us put one item in front of the other, what the optimal algorithm does the reverse, we would see an inversion. But it has some details, how the definition of inversions, that I would refer you to the full version of paper for those details. And another part, which is relatively the harder part to do, is to see how we can handle insertion and deletion operations. And here where our well-behaved request sequence come into play. So the question is, what's the good size of this? What's a well-behaved sequence? And so here we say we want to consider request sequences that don't have insertion and deletions too often. They happen after a while, these insertion and deletions of items on servers. So that's a well-behaved sequence, and the question is how we can define this well-behaved sequence, and the answer depends on the expected length, maximum length of each server list. So if we can find that expected length, then the rest we can amortize the cost of insertion and deletions of servers and items given this expected length. So to quickly go over the empirical results that we had, first of all, we use the recommended parameters of the algorithms. So 1.25 for the algorithm that was suggested by a team from Google, and +4 for our algorithm, and we see we can get a much better storage utilization with a bit more access cost compared to the traditional algorithm. And on the other hand, this is what we heard from the practical point of view. Sometimes we want to fix the capacity, and for the fixed capacity, the traditional algorithm might not be able to tolerate that fixed capacity, because when it reaches when the number of items reach that fixed capacity, can not go over that. So it would fail at some point, but because our algorithm and the with bounded load algorithm can move items around, they can thread as many items as the sum of the capacity will allow. But here we can see that our algorithm, the access cost of our algorithm, is much better compared to the with bounded load algorithm. We have many more empirical insights in our full paper. So thanks for listening to me. In the future, we want to go and implement our algorithm as a part of the HA project, which is an open source load balancer. And we also want to extend the idea of self-adjusting to other distributed algorithms.